So data registers are used to hold data for arithmetic calculations. So here's an example of a 2-bit data register. It uses 2 negative edge triggered D flip-flops, and I'll show you how it is used to hold data for calculations. Okay, so D0 and D1 are the inputs, and R0 and R1 are going to be our outputs. And we'll try to see how providing specific inputs to D0 and D1 will show up as outputs at R0 and R1. That's what the data register is going to do. Now, before we do that, it would be good to remind ourselves what the D flip-flop truth table looks like, because that will be used to understand the circuit. So I'm just going to redraw the table for the D flip-flop. Okay, so we can have 0 and 1 as inputs to the D. Since this is a negative edge triggered flip-flop, we are interested in the negative edge. And then the outputs are going to be 0. So it's pretty much follows the D, and 1, 0. And for anything else, for the X, you could have 0, 1, or a positive edge trigger. The output remains unchanged. So Q is Q0 and Q0 bar. Okay, now as I said, this particular register is used to hold data for later consumption, so for arithmetic calculations. So if you provided certain inputs to D and D1, it will show up as outputs at R0 and R1. So what you need to do is the following. Let's assume that in this case, let us assume D0 was 1 and D1 equals 0. These are our inputs. Okay, so we provide these inputs, and let's see what happens to the outputs. So if D0 is 1, let me put it here. And this is 0. So D is 1. What will happen is when the clock is negative triggered, negative edge, like so, we'll see that the output would be 1, right? So this output would be 1. So this is 1. Okay, let's do the same thing for the other one. When this is a negative edge trigger, this output, so 0 is the input, negative edge trigger, output would be 0. Okay, so that output appears across the AND gate. So we have 1 and 0. And in order to read this, in order to get a meaningful output from R0, all we need to do is we need to set the read pin to 1. This is an input. It only is queried when you want to read something. So we'll put 1, which means this is 1, this is 1. And since this is an AND gate, the output would be 1.1, which is 1, and 1.0, which is 0. So what you see is that this input shows up here, this input shows up here. And remember that it only shows up when we provide only true when there is a negative trigger. It will not work if there's no negative trigger. So the register is basically ensuring that 1 and 0 are saved at Q0. Remember that flip-flops remember their values. And so they'll remember this value Q0 and Q1, which is 1, 0, the same as what we provided as the input. And all you do here by putting this 1 is to read it. So this is how a data register can be used to remember, hold the value and read it. So when read, okay, so I'm just going to put this in words. So let's assume this is true. When CK goes negative or the negative edge trigger, we would have Q0 would be 1, Q1, which is the other output, will be 0. Setting read to 1 will let R0 to be 1, R1 to be 0, just like I described. And this is our output, which is the same as input. And this is basically the function, register, data register function. You can also note that, as I said, Q0 and Q1 is the output across the flip-flop. And remember, this is remembered. Holds this output. Okay, so let's now go to the next application of flip-flop, which is a binary counter. You want to essentially count numbers from, I don't know, 0 to 1,000 or something like that. You will use a counter. Now, this one is only going to count till 3 because I've used 2 flip-flops. Each flip-flop can output 0 and 1. The combination of 2 flip-flops can do any 2 combinations of 0 and 1. So it will be 4 outputs, which would be correspond to 0, 1, 2, and 3. If you want more outputs or count more numbers, you need more flip-flops. In fact, if you want a certain number, then you need to use this formula. With n flip-flops, you will get 2n minus 1, 2 raised to n minus 1 count. Okay, so you can use that number to construct this. And this is very extendable. You can just take this and just add more T flip-flops and you'll get what you want. Okay, so this is a T flip-flop. And what we're going to do is we're going to try to understand how this flip-flop enables us to count from 0 all the way to 3. Okay, as before, I'm going to write the truth table for the T flip-flop because that will help us to analyze this. So the T flip-flop has this truth table. Okay, so this is, if you see the symbol here, it is a negative edge triggered flip-flop, which means that it'll only be triggered when there's a negative edge. All that the T flip-flop does is it toggles the output. So Q, whatever that is, will become Q bar on the negative edge. And it will keep on happening as you give more negative edges. If you give anything else, like 0, 1, or a positive edge, the output is unchanged. Sorry, Q. Yes, I'm just doing that because I'll use this in order to analyze this. Okay, so so remember our goal is to count from 0 to 3. So here are the steps. So before you start counting, you better ensure that all the output is 0. So what you do is you set the reset to 1, which basically sets B0 equals B1 equals 0. So it's resetting all the values. And now we can start counting. So what is going to happen is we will be doing something like this. So this is going to be the input. Okay. And based on the input, you need to be able to count. So in this case, this is the negative edge trigger flip-flop. So what will happen is the following. Whenever it hits the negative edge, something is going to be triggered. So this edge, this edge, this edge. So let's look at the output. Let's look at Q0. Okay, I'm going to draw, well, this is 0 and 1. So I'm going to draw the output of the first flip-flop based on this truth table. So initially, we know that it's set to 0 based on the reset pin, so it's 0. Now, what this truth table says is that it's going to be triggered when the first negative edge trigger happens on that flip-flop, which is going to be T0, which is, by the way, this one. So the first edge is here. So this will remain 0. The moment it sees the first negative edge, it's going to toggle, right? Go from 0 to 1. Okay, then it'll remain 0. The next negative trigger, it'll go down, remain 0, go up, go down. Okay, so that is my Q0. Now, what you notice here is that Q0 is the input to T1. Okay, so Q0, so T1 is triggered based on Q0. So you can apply the same kind of logic for T1, where the input is Q0. And we know that the T flip-flop is triggered on a negative edge to the input. So the negative edge we're seeking is the negative edge for Q0. So those negative edges are here and here. This is Q0 or T1. So let's see how this will be activated. So we need to look at Q1. Remember, it starts at 0. Okay, now it'll remain 0 till it sees the first negative edge on T1. So here it will go up. And then here, since it's again going down, it will follow that, go down. Okay, so now what remains to be shown is that this actually is able to count the numbers from 0 to all the way to 3. Okay, so B0 and B1 are the outputs, and they correspond to Q0 and Q1. So this is nothing but B0. This is B1, because B0 is connected to Q0 and B1 is connected to Q1. So let's see what happens. So here, the best way to show this probably this way. So up to here, this trigger, and I think I'll write it in the words, that way it's very easy to understand. So let's write B0, not the graph, but as numbers. So here B0 would be 0, because B0 is nothing but Q0. Here B1 is 0, so both of them are 0. Let's look here. Here we have B0 is 1, B1 is 0. Here we have B0 is 0, B1 is 1. this one. And then finally here we have 1 and 1, 1 and 1. Okay, so if you look at this combination, this is 0, 0, or the number 0. Okay, this is, it depends how you interpret this. If you interpret B1 is the first bit and 1 is the second bit, this is same as 1. This is 0, 1, so it's going to be, oh, sorry, 1, 0, it's 2. And this is 3. And after this, if you keep going, it'll actually reset to 0, and so on. So this is how you can use the binary counter to count. Okay, let's look at another application. Okay, it's called a serial to parallel converter. Serial here, what we're trying to do here is we have one single input, and we want both the outputs to be the same as the inputs. An example of this would be if you have, I guess this is not a digital world example, but in real world, if you want a switch to turn on two lights on simultaneously, you are essentially looking at a serial to parallel converter. That one input that is turning on one switch will turn the lights on in two places or two rooms or two places in the same room. That would constitute a serial to parallel converter. You could do the same thing with flip-flops, as I'll show you next. Okay, so this is a circuit involving the two D flip-flops, and we are trying to understand how the P0 and P1 would change as the serial input is changed from 0 to 1. So let's do the same thing as we've done before. Let's remind ourselves what the truth table for a D flip-flop is, which will help us to analyze this circuit. So a D flip-flop has D, CK, Q, Q bar, so D can take zeros and 1. Since this is a negative edge triggered flip-flop, we're only looking at the negative edge for the clock. When D is 0, Q will be 0, hence Q bar is 1. When D is 1, Q is 1, and Q bar is 0. And for any other input to D, X or 0 or 1, we'll also write it as 0. Just do it X is 0 or 1. And no matter what you put for the clock, 0, 1, or a positive edge, the output is unaffected. So it's Q0, Q0 bar, that it remembers its previous state. Okay, now let's try to understand how this flip-flop works. If you want, you can reset the flip-flop by setting in reset equals 1. This is only if you need to do that. Okay. So next step is we're trying to understand what would happen if you provide an input to serial. Let's say that the input is turning a light on. So we want to say turning the light on is serial equals 1. Okay, so we are trying to understand what happens to P0 and P1. So let's look at the truth table and the figure to understand this. Okay, so when serial equals 1, okay, and assuming that the clock achieves a negative edge trigger, so assume that there's a negative trigger, we would immediately see that Q0 would be 1. Right, from this. So we know that Q0 would be 1. Okay, but what we also see is that the same clock is triggering the second flip-flop. So when this goes, achieves a negative edge, this one will also have a negative edge, and this one would affect D1. So Q1, D1 would also be 1, and hence Q would be the same as D. So Q1 will be 1. So we see that P0, because Q0 is 1, P0, which is the output of Q0, is also 1, and P1 is also 1. So what we observe is when the input is 1, the output is 1 and 1. In effect, the switch has turned both the bulbs on. Okay, and you can use the same logic for similar logic for serial equal to 0. So you can do the same thing, and you'll see that P1 and P0 would be 0. Okay, so let's look at the reverse of a serial to parallel converter, a parallel to serial converter. Here, our goal is that we want to get the serial output to be 1. Serial output is green for any ones achieved in the parallel output. What I mean by that is, I don't know if you might have seen this kind of system. Usually on a staircase, there are 2 switches, one switch downstairs, one switch upstairs, and they are used to turn the light in the stairways off and on. So you would like to, for example, turn the switch on when you're downstairs, so you can see the stairs, climb up. When you go up, you want to turn off the lights by turning on the switch which is upstairs. And so both those switches do the work of turning the switch on and off based on sort of this concept of parallel to serial. You want to control something from 2 places, okay? And so this is the solution for you. So as you see, this one uses a JK flip-flop. And so what we'll do is we'll draw the truth table for the JK flip-flop and then try to understand how this works. Okay, so preset. So I'm going to take a subset of that, not everything, because we don't need everything. So preset 0, 1, 1, 0. So no matter what the preset is, this one will always give me 1, 0, 0. Sorry. Yeah, 1, 0, 0, 1. It doesn't really matter what these inputs are. So that's the goal, is to clear the outputs. Okay, now we have 2 more cases. Okay, now let's just put 1 and 1. This is the normal operating mode of the JK flip-flop. Let's look at the negative edge trigger because this is the negative edge triggered flip-flop. Let's take just 2 cases, 1, 0, 0, 1, because that's all what will be needed here. 1, 0, 0, 1. This is just for initialization. Okay, so let's see how this works. First, what we do is, let's say that we just want to clear, we want to turn all the lights off. So we will put load equal to 0. Okay. If load is 0, no matter what P0 and P1 is, this NAND gate will output a 1. When it outputs a 1, the PS becomes 1, and the preset becomes 1, and the effect of setting the preset to 1, and assuming that the reset is set to 0, is that we get a 0 and 1 across the output. So we will have Q0 is 0, Q1, which is same as the output S1 is 0. Here, the flip-flop here is reset. So I should put the consequence of this is this fact, and the consequence of this so this is the consequence of load equals 0, and then the consequence of PS0 and PS1 is okay. So flip-flop is reset. Okay, now step 2. Now let's say that the normal operations. That was the initialization. We always set the clear pin to 1. Okay, so clear is set to 1. Clear is, this is just the clear. We have this, oh, sorry. Okay, so normal operation clear is set to 1. Now what we can do is we will set the load to 1. Okay, and now we'll try to understand how this combination will work when CK gets the negative edge. So this clock is powered by a separate input, but it is the same clock is powering both the flip-flops. Okay, there are 4 cases. So I'll talk about the 4 cases now. The 4 cases are okay, so the 4 cases are the different combinations of P0 and P1. You could have P0, 0, P1, 1. Sorry, did this move? Hold on, fix this. Okay, so you could have P0, 0, P1, 1. You could have 0, 0, 0, 1, 1, 0, 1, 1. So we need to look at all those 4 cases and see what this output S1 is for those. And that will basically be all that we need to do. So case 1, P0 equals P1 equals 0. Okay, so let's put 0, 0 here. So we know that this load is 1, but really doesn't matter. Whatever 0 times 0 is always going to be 0, and then we need to invert it. So this will be 1. This will be 1. Okay, now if the preset is 1, clear is 1, and there's a negative edge, it all depends on what J and K is. Now, here's the thing, which I sort of forgot to mention. For this particular configuration, we always keep the first J0 to be 0 and 1. It's always the case. If we don't really make it as an input, we fix it to 0 and 1. So in effect, we are only looking at this part of the truth table. Okay, so if that is 0 and 1, now we need to understand what Q would be. It would be Q0 would be just 0. So this is 0, and this has to be 1. Okay, now this 0 goes in here, and this 1 goes in here. Okay, now we have J1 equals 1. So I'll just write it down. So since J0 equals 0, K0 equals 1, a consequence of this is that Q0 equals 0, but that is same as J1, which is 0. And then Q0 bar is the same as K1 equals 1. Okay, so if J1 equals 0 and K1 equals 1, we again look at the same row of the truth table. It means that Q would be 0, right? So Q or Q1, so a consequence of this is that Q1 is 0, which is the same as S1. So what we notice is that for these inputs, S1 is 0. So if no switch or no switch is turned on, both the output will be 0. Okay, but we need to do this truth table and this chain of reasoning to figure that out. We can now look at the second case when P0 is 1, P1 is 0. Okay, now let's reason this out. Let's put P0 as 1, P1 as 0. Sorry. Yeah, that's right. Okay. Now, load is 1, P0 is 1, 1 times 1 is 1, but this is the NAND gate, so this will be 0. Similarly, we have 1 times 0, which is 0, and so the output here would be 1. Okay, next we need to look at what the truth table looks for a preset of 0, and JK can be anything. So clear is 1, as we have put over here. Preset is 0. So we see that the output Q is 1. So PS0 is 0, PS1 is 1. A consequence of this is that J0 is, sorry, my bad. Since J0 equals 0, K0 equal 1, that is, this doesn't change. Okay, so because PS0 is 0, we would have Q equals 1. So Q0 is 1 because of this row. And hence Q0 bar equals 0. So now the inputs to the next flip-flop are 1 and 0. Okay, now let's look at what happens next. So we have, for the second flip-flop, 1 is the preset, 1 is the clear. So we are looking at one of these two. J1 is 1, K1 is 0. So J is 1, K is 0. So we are looking pretty much at the third row. So 1, 0 would be 1, 0. So the output would be 1 and 0. So PS1, J, so Q0 is the same as J1. Q0 bar is same as K1. And the consequence of this too is that Q1 would be 1, Q1 bar would be 0. But Q1 is the same as S1. And that's what we were trying to achieve, which is when yellow one. What we're trying to achieve was when one of these switches was turned on, so P0 was turned to be 1, the output S is on. And that's what we were after, if you got that. Now you can do this. So I just took 2 cases, but then there is a third and fourth case, which I will just write down here. And then I would like you to reason it out yourself. And that case is, if you have the third case is, what if P0 is 0, P1 is 1, speaker is home. So what you should have is that S1 equals 1. And then the fourth case is if P0 was 1, P1 was 1, then you'll also have S1 equals 1. So I would like you to figure this out yourself, just like I did it for the first 2 cases. That is, what this says is that when any of those 2 switches is turned on, that is P0 or P1 is on 1, S1 is 1. Thus, S1 is 1. As long as one of P0 or P1 equals 1.